Amadeus.
The science guy.
Amadeus.
The science guy.
Amadeus. 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 Amadeus.
The science guy.
Science rules.
Amadeus.
The science guy.
Inertia is a property of matter.
Amadeus. 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 Amadeus.
The science guy.
Amadeus. Amadeus. Amadeus.
T minus
Amadeus. 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 Amadeus.
The science guy.
Oh, hi there. Didn't see you there. So, today we're going to be talking about the differences between extraction and washing. And a good way to do this, or a good way to illustrate it, is perhaps using an example of making tea. So, we can go make a tea real quick. Right, so why do we go make a tea? Well, tea is a great example of an extraction, where in the tea you have flavors and different solubles that you want to drink and you want to end up in your tea. And then there's other things like the solids that you don't want in your tea. You don't want like a grainy and a chunky tea, or perhaps some bitters in there. So an extraction is mixing a compound in a solvent in which the thing you want, the flavor, is more soluble in that solvent. So when you end up pouring it out, you save that liquid, that solvent, with what you want in it. And the main difference between extraction and washing is that, for example, washing, when you're washing perhaps this mug, when you're done with it, you are getting rid of the material that's in the solvent. So whether that be grease or fat or perhaps any leftover materials in there. So that's the main difference. One, you want to keep the material that's in the solvent, and the other you discard. It's unwanted. All right, so now we're going to be discussing with models extraction versus washing. So as per requested, here is another look at the beautiful student ID. All right, without further ado, let's get on to the model. All right, so this is the washing method model. So here we have a solvent. We have a solvent here, and then we have a compound which we want to wash. So washing is the process in which you remove something that you don't want from a different compound using a solvent. The one caveat that has to be mentioned for that is that the unwanted material has to be more soluble in this solvent than in the mixture that it's already in. So what we end up doing is we want to get rid of these black balls, and these are what we want to have left over. So what we're going to do is mix this with a solvent, and because the solvent is going to be immiscible with the mixture, we're going to end up having is that what we don't want is going to stay with the solvent, and the rest of what we actually want will stay out. So we can separate the two and get rid of the stuff that we don't want. All right, so this is the extraction model. And as showed earlier, making tea, extraction is where you pull something you want out of a compound and you keep that material. So let's use, this time the white balls are going to be what we want. And we're going to use a solvent. And so think about this in terms of the tea bag. So the tea bag goes in with everything we want, right? And as it's steeping, we have the white is going to be staying in, to be more soluble in the solvent, so in the water. And so when we pour the water out, what we get is the tea, all the flavors and whatever else is in the tea that makes it really delicious, stays in the water, whereas we can discard the solids and other materials that we actually don't want. All right, so now I'd like to talk about the separation of a homogeneous mixture of three unknowns. So for the one that I'll be discussing, it'll be number 2, which is composed of equal parts of anthracene, piperidine, and oxalic acid. So in order to properly set up an experiment in order to separate these and isolate them in the purest forms possible, you have to know a little bit about their physical characteristics. So if you look up here, you can see a table that shows the different solubilities along with the melting points and boiling points, etc. of each particular compound. So by looking at these, we can ascertain as different methods for removing each component. So if you notice, anthracene is insoluble in water completely, whereas both the oxalic acid and the piperidine are soluble. Piperidine being much more like fully soluble and oxalic acid partially soluble. In order to get around this, we can add all three, this solid, into a mixture of just water and heat it up. So what you'll do there is dissolve the piperidine and the oxalic acid into solution, whereas the fully insoluble anthracene will stay in solid form crystals. So what you can do then is remove via gravity filtration the anthracene. So normally a good method to separate materials like this is using distillation, and we in this laboratory went through simple distillation. And the one problem with simple distillation is that you require a boiling point difference of no greater than 100 degrees. And there's also a challenge involved with having a simple distillation in which your solvent has to boil over 110 degrees. So piperidine and anthracene and oxalic acid, if we had a solvent that we could dissolve all three in, and had a boiling point perhaps above 100 degrees, then you might be able to do a distillation in which you could boil off one of the three. The lowest one being piperidine, so that would be the one that you would boil off and have condense into another beaker. However, because anthracene is not soluble in water, and even if it were, water has a boiling point of 100 degrees Celsius. So if you try and reach the boiling point of one of these three unknowns, you actually end up boiling off the water before removing any of the other compounds which you actually want to isolate. So now if we've gravity filtered the anthracene out of solution, we will be left with water and piperidine and oxalic acid. So if you look at the solubilities again, you can see that piperidine is fully soluble in diethyl ether, whereas oxalic acid is not. And it is still soluble in water. So what you can do is mix these in an extraction. So you can extract the more dense layer by mixing with diethyl ether. And if you were to add a base, perhaps sodium hydroxide, so you have an hydroxide ion, you can actually create an oxalic acid salt, which will be more soluble in the water and want to stay in that layer. So the point of an extraction here is to have two miscible layers, in which each one of your compounds resides. So in this example, your piperidine will be in the organic layer, which will be the diethyl ether, and your oxalic acid will be residing in the aqueous layer. So by doing multiple small volume extractions, you can thereby isolate the two. So you want to remove now the water and the diethyl ether. So if we want to separate the diethyl ether, like the organic layer, from the aqueous layer, as we're using the stopcock in the separatory funnel, the more dense layer will be the bottom layer, and that is the aqueous layer, because water has a density of about roughly 1,000 kilograms per meter cubed, whereas diethyl ether is about 716 kilograms per cubic meter. So when you're extracting, you'll end up having the aqueous layer come out first. So once you have the aqueous layer, you can set it aside, and then you're going to add a drying agent to the organic layer, because you want to be able to get rid of as much of the water as possible. So when you put in a rotary evaporator, you can evaporate off the solvent. So a good choice of a drying agent is anhydrous sodium sulfate, as it's cheap and neutral and generally works quite well. So putting that into the organic layer should remove any excess water. You can let that sit for about 10 minutes to absorb any remaining water. From there, it goes into the rotary evaporator, and the rotary evaporator uses vacuum to lower the temperature needed to induce boiling in the solvent. So that solvent is then washed and removed into a separate beaker. So now moving on to the aqueous layer, which contains oxalic acid, you can add some sodium hydroxide pellets over heat and make sure to stir constantly. And so once they've dissolved, you will begin to have a precipitate of oxalic acid. You can then use vacuum filtration to further isolate the oxalic acid. All right, so today we're going to be talking about the organic synthesis lab that was performed and the procedure that goes into actually making the 2-butoxynaphthalene, which is a flavoring agent used for raspberries and strawberries. Or at least that's the flavor it kind of makes an industrial scale. So to begin with, you're going to add about 0.5 gram of 2-naphthenol to a flat-bottomed round beaker. And you're going to add a magnetic stir bead in there as well, along with 2 sodium hydroxide pellets and 95% ethanol. So you're then going to put this on a hot plate and reflux it, which is essentially boiling it, making sure to have a condenser on top of this vial, and stop it. So you stopper it so that you don't lose any of the solvent due to evaporative means. So you're going to put that on. All right, so then you're going to put it on a hot plate and you're going to boil this mixture, reflux it, until the solids are dissolved. When you've been refluxing this for about 15 minutes or so, you're going to add, with a micropipette, which is quite expensive, 50 milliliters of 1-iodobutane. So you're going to take off the condenser and you're going to take off the heat and you're going to add the iodobutane and you're going to put it back on, making sure to put the condenser back on. You're then going to reflux that for 1 to 1.5 hours. And just before you take this off, when it's completely done, you're going to take a very small sample and you're going to do a TLC analysis. So in a 1 to 3 hexane solution, you're going to put this with a co-spot, and you're going to measure under UV light and circle your findings. From there, we then are going to have to put this over ice. So you're going to measure out a certain amount of ice solution, and you're going to put that over the reflux material. Make sure to keep it very, very cold, because if you keep it any warmer, you risk losing quite a lot of the 2-butoxynaphthenol, which is what we want at the end. So once it's been quenched over ice, you can then pass it through a vacuum filtration setup in order to isolate the final product. All right, and lastly, once you have isolated your solid from the vacuum filtration, you're then going to measure it first, how much the yield you've gotten, and then take a very small amount of it and put it under the IR spectral analysis machine to actually get a reading for the spectra that it produces. So you can compare it to a known standard for 2-butoxynaphthalene. All right, so now we're going to be getting into the analysis of the product of 2-butoxynaphthalene that we created. We're going to use the IR spectra data that we had collected and also look at the TLC plate that was made. So we're going to just scoot over here. All right, so looking at the spectral data that we have available to us, one collected at the very end of the procedure where we use vacuum filtration to isolate the crystal solids of the 2-butoxynaphthalene. We have a broad strong signal at around the 3000 wave number transmittance, and also some sharp peaks at around 1600 and 1630. So as you can see, I pulled up from the spectral database of organic compounds, the 2-butoxynaphthalene standard IR spectral analysis. And if you compare the two, they look very, very similar. In fact, if we look at the wave number and transmittance values side by side for the two, we see that they're all less than 1% difference between the two of them, which is very good. It means that it's very likely that these are the same material, and that it's also quite pure, which bodes well for our experiment, because that was the idea, was to synthesize this 2-butoxynaphthalene. So because this was done at the end of the experiment, it means that the pure product at the end is looking to be very strongly, that suggests that it is indeed 2-butoxynaphthalene. So now if we look at the TLC plate analysis, and keep in mind that we took this TLC sample before pouring it over ice and quenching the solution, which helped us get a good yield of the 2-butoxynaphthalene. So when we took the TLC, it was just before it was done in the reflux stage. So if you look at the TLC plate, this is a rough sketch from the video that was shown online. So we see that in the R lane, which is the lane in which we placed our sample, and then the co-spot lane is a combination of our sample with the standard which we wanted to compare it to. And we used a acetate hexane solution, 3-to-1 ratio. So we see that there's one spot in the S lane, which was our standard, and there are 3 more or less distinct points in the co-spot and R lanes. So as mentioned earlier, if you have more than one spot in a TLC plate, that normally means that there's more than one compound present. So we can see that there are more dots in the lane, which we would expect if there was only one compound. So at this stage, it's more than likely that there are other compounds present in our solution. All right, hello again. So today we're going to be discussing the reaction that the third experiment underwent, and I'm going to use some models here. So the process was use 2-naphthenol and sodium hydroxide and ethanol along with a iodobutane in order to produce 2-butoxynaphthenol, which is a flavoring agent in strawberries and raspberries, I believe. So here we have 2-naphthenol with the OH group here. So red is the oxygen, white here is the hydrogen, and then we have the iodobutane, where the purple one here is the iodide. Additionally, we have a sodium, positively charged, and an OH group here, negatively charged. So this here, there's 2 steps involved. The first being the deprotonation of the OH group. And so that happens primarily with the negative charge on the OH here. So this negative charge will attack this hydrogen, and that charge will get transferred to the oxygen here. So pops off, and we now have an OH in solution. So what that leaves us with here is a methoxide ion, negative charge, a positively charged sodium, and water. So by adding in the iodobutane here, this negative charge is going to be transferred via SN2 mechanism to this carbon here, which will then bump off the iodine into solution. So you'll have a negative ion in solution for iodine. So what that looks like is this popping off. So then we get the 2-butoxynaphthalene which is the flavoring agent. In the solution we have water, positive charged sodium, and a negatively charged iodine. Alright, so today we're going to be talking about the different techniques for purifying and characterizing solids and liquids used in the chem laboratories. The first one would be a melting point determination, and what it's good for is determining the purity of a compound. So what that means is the smaller the melting range from the onset to the clear point, it generally means that it's a more pure liquid, the narrower that range. For every degree difference, it's approximately another percent impurity in the actual compound. It also helps us narrow down the particular solid because solids have very specific melting points or melting point ranges, so it can help us to identify different types of solids there. The second one we're going to talk about is distillation. And there are a couple different types of distillation, though the one we used in the chem labs was simple distillation, which the one caveat for that is the difference in boiling points between the two substances you're looking at can't be greater than 100 degrees Celsius. So the idea is to reach the boiling point of the lower compound, thereby removing it via evaporation. So what happens is you evaporate off this the lower boiling point mixture, and as it goes up, it gets condensed in a condensing tube and then pushed into a different beaker. There's a problem with having something with a boiling point perhaps above 110 degrees Celsius, as you need to have it in a solvent. One solvent used is water, which has a boiling point of 100 degrees Celsius. So having something over that boiling point means that you're going to boil off the water, evaporate it off, and distill it before the actual solvent that you want, or solution that you want rather. So recrystallization is used to purify a compound. In the chem labs, we had a compound that had impurities in it. I think there were some wood chips along with other materials in there. And in recrystallization, there's a couple steps. The first being the choice of a solvent. You want a solvent that isn't going to dissolve your material at room temperature 100%. You want to be able to heat it up and then have it dissolve. So it's a pretty important choice to make is what solvent you're going to use. So once you have chosen a solvent, you're then going to filter it once you've heated it up. So you heat it up obviously with a magnetic stir rod or bead so that you don't have any bumping happen. So once it's all dissolved, you're then going to filter it via gravity filtration. And it's important here not to use a stemmed funnel, rather use a stemless funnel, because you don't want crystals to form inside the funnel. And to also prevent a lot of evaporative loss, you're going to put a watch glass over top of the funnel itself. So once it is cooled in the beaker, you want to let it cool to room temperature, because by cooling something too fast, you can actually create very small crystals in solution. And what this does is it traps a lot of impurities. If you let it cool too slowly, what happens is that you have large crystals, which also can trap impurities. So you let it cool to room temperature, and then you immerse it in an ice bath. And you can agitate it slightly, and this should induce crystals. If nothing happens though, you can scratch the inside of the glass using a glass stir rod, and this shaves off slight bits of the glass itself and actually gives a rough surface for the crystals to form, so it can help induce crystallization. So just quickly, I forgot to mention the point of recrystallization here is actually to isolate that pure compound, because we've now dissolved all of that the compound in a solvent, and we filtered out perhaps the large chunks that were in there to begin with, and all the material, the solvent, is now also filtered off. So what we're left with is just the pure crystal compound, which we wanted to isolate in the beginning. So we're actually just purified that compound. The next technique we use is thin layer chromatography, or TLC for short, and it can be used for multiple things. It can be used to assess the purity of a mixture, the identity of a component of a solution, or even to gauge the progress of a reaction that's happening. So what is the TLC plate? The TLC plate is an aluminum backing with a silica gel that's spread or sprayed on. And so what you do is you first have to get a very, very small amount of the solution onto the plate itself. So you can take a very small capillary tube and run it over an open flame and pull it apart, so you get a very small microcapillary. You then take a small dot of your unknown, or the solution you want to look at, and you dot it on about 1 centimeter from the bottom, and then you would have a standard or something you wish to compare it to, and you do the same on the opposite side. And in the middle, you put both. You put a co-spot, one of each solution. This is to measure the difference between the two, so you can see both. You then have to choose a solvent you want to put this in. And this solvent choice is also quite important because the polarity of the solvent actually determines the RF value, or the ratio between the solvent front and the dot you'll be observing. So if you have something that's too polar, it might cause for the ratio to be too great. So what happens is you immerse it in this solvent, and as the solvent front moves up, these spots actually get carried up the TLC plate. About when there's about 1 centimeter left of the solvent front, you remove it from your beaker, and you shine some UV light on it, and this helps you distinguish the actual dots themselves. So you then would take it with a pencil and circle the dots so you can see it without UV light consistently being shone on it. So when it's assessing purity, in each lane, there should only be one dot normally, if there's only one one compound present. If there's more dots in the lane, then you'll more than likely have an impure substance in there. So the point of having this co-spot is to see if these RF values, or the ratio between the solvent front and the actual compound, is to see if they line up. So if you have two that show the same pattern, it's a pretty good guess that they're going to be the same material. You'd also compare it with different techniques, but it's one of the techniques that can be used to identify a compound. Moving on, we have an IR spectral analysis, and it can be used for either solids or liquids. In the laboratory section, we did it for both. And it can be used to identify the major functional groups by looking at the absorbance at different wavelengths or wave numbers. So for example, an OH group will have a very large, broad signal, strong, at around 3000 wave number, which is due to the stretching of the bond, there's a certain absorbance associated with that. Lastly, I want to discuss extraction washing, which I've given a little example prior. This is a little more in depth and procedure. So washing and extractions help us separate two substances based off of their density and also their relative solubility. So the idea is that these two substances will reside in two immiscible phases, such as an aqueous phase and perhaps an organic liquid of some sort. The two are then mixed and allowed to settle, and the denser layer will be present on the bottom and the less dense layer will be on top. So using a stopcock, you can pour off the more dense layer, and it is preferable to do multiple smaller volumes of this rather than a couple large big ones, because you'll get a better yield at the end by doing smaller, more iterative volumes. The non-aqueous layer is then washed using a sodium hydroxide solution, and being non-aqueous, you want to get rid of as much water as possible. So what you do is you use a drying agent. And a drying agent, there's multiple different types you can choose from, and it is also important because some are more expensive, some are cheaper, some will react with acidic solutions, some basic. So You have to look at the drying agent you want to use and make sure it lines up well with what you're washing. So you place this drying agent in there, and again, you have to look at what drying agent you're using, but you'll see how long it needs to dry for. So it's going to absorb the water out of the solution. And then, once all the water is removed, you can put it in a rotary evaporator or a rotovap. And what this does is it evaporates off the unwanted solvent, so you're left with the compound that you began with that you want to isolate. So rotary evaporator essentially works by trying to evaporate off this solvent, boiling it under vacuum. So that means you can use a relatively lower temperature to induce boiling of the solvent. And that solvent is then transferred to a beaker and discarded later, which is what washing is. You're getting rid of the solvent. And additionally, so for some solutions, you can actually basify them by using sodium hydroxide pellets. And the solid will then precipitate out a solution, and you can then isolate that with like a vacuum filtration system. So that's a brief overview of the different techniques that are used in the chem laboratories. Very, very useful to determine the properties and also the identity of some solutions.